welcome everybody who decided to participate in Sano seminar today remotely. Decided, or sometimes, as me, was forced to attend remotely. And well, today we have as a speaker we have Luca Gherardini. Luca Gherardini from computational intelligence team, led by Jose Souza. I think that we, in a moment, I will give floor also to Jose, just to say some words about research which is performed by Luca. And Luca holds a Master of Science degree in computer science from Italy, from University of Modena and Reggio Emilia. And recently I think that he is practically at the end of the process of obtaining a PhD in medicine from Queen's University Belfast. Well, it is a very complex procedure, so probably graduation is organized for all PhD students. So, but we consider Luca as a postdoc at Sano. And today's seminar will be about the research which was in his PhD thesis. Well, that's, I think, all from my side. I think that, as usual, during seminar, you can ask on questions and answers and on chat the questions which need emergent answer in order to understand what is presented. And of course, as usual, we will have discussion after Luca's talk. So, Jose, would you like to tell something about about Luca's research?
I can say a couple of words. So I'm really proud that Luca arrived here to this point where he's a postdoc to be. It was quite a bumpy road, so we had a couple of things around the process. We finally did it, and I'm really proud because he's got his PhD in medicine, so he's even better. So it's an add-on on his research. Yeah, and this project started as a tool or a new AI approach, and then end up being applied to a very specific disease that Luca is going to describe and how we address it, because we are lucky to have a good data set to explore a couple of problems that we had. So yeah, but Luca did a fantastic work. He already submitted the correction of the thesis, so we are just waiting for the final approval of Queen's University, and if everything goes well, in 2 months, I would say, he will be able to have his degree and his PhD in medicine. So yeah, well done, Luca, and
I think that Luca is not only active in research, he is also, together with Rosemary, working on something what you will, I think, will see in 2 months from now, something like this. So
yes.
yes, so it is a very active person. We are very proud of in Sano of having Luca with us. So Luca, floor and screen are yours.
Go. Okay, thank you, and hello everyone. I'm going to share the screen so everyone online can see it. Okay, so the title of my thesis is Towards Collaborative Computational Models for Predicting and Understanding Complex Degenerative Disease Trajectories. It's quite long, but because it comprises a lot of different areas, a lot of different things. This PhD was joined by Queen's University Belfast and Sano. So these are my 3 supervisors. So this took quite a lot of supervision, expertise in different areas, and a lot of work, definitely. The mission we had was quite straightforward. we wanted to have a classification method that was able to classify even in presence of fragmented, noisy, and small data sets. So we wanted to move a little bit against the general tendency of using big data, having these big models with a lot of parameters, able to extract all these complicated patterns, but requiring also big amounts of data. We wanted to move in the opposite direction and providing something that was able to work a much smaller scale without losing accuracy. So, as we said, there were some constraints that we chose to solve in machine learning, which was the problem of data hunger and also the problem of explainability. So we wanted a classifier that was able to perform with very limited information and also being very simple and explainable. So we propose an approach that is called Cactus, a classification and abstraction tool for uncovering structures. This is the pipeline of the tool. So we're starting from the raw data, and each feature is abstracted using a rock distribution, meaning that continuous values like 10, 11, 15, and so on are translated in up and down flips. So these are discrete representations of what the variable represents for the class we are considering. So we go from a continuous space to a discrete space. This is useful, which will be here, right? So we see all these features abstracted into symbols. This is very useful because it allows us to reason a little bit more intuitively. So we can say that a person has high blood pressure or low cholesterol, or is young or old with respect to a disease. So we can start to characterize the patient in this case in terms of healthcare data in more intuitive terms. This also allows some nice properties. So for example, we can do a filtration of the features that are not informative, and we can link features together into knowledge graphs, where this means that we start to find patterns in every class that describe how these discrete elements are interacting. So if people that are old and are smokers, for example, are more likely of having a certain disease compared to people who are not smoking or who are younger. And this allows us to build a significance profile, which means that essentially we have a class described by what is more important in it, what is more relevant, what is more connected to the rest. So it's a graph perspective on a class, a graph description of a class. Having these profiles allows to do classification through, which is here, through pattern matching. So essentially, we can compare a patient record like this one with the significance profile of each class, and this will give us a score, meaning that it will tell us how similar this patient is to each of the class descriptions we have, and we assign the most similar one. This is also quite intuitive because it allows also to understand how close the patient is to each of the classes. And also we can have ranks, which means that we can also, the model can tell us what is more relevant for the classification process. And this is quantified by seeing the different distributions of data across the classes. So you can say, for example, here you can see that there is almost a 50-50% between up and down flips in the class 0. But when you go to class 1, everyone had, or almost everyone actually, had the up flip. So had overexposition to something, had an overexpression of something. And this is very informative because this tells us what's happening, what is the transition from one class to the other. And this is called a rank, which is also accompanied by a number that allows us to sort the features by this metric, which means that we can see exactly in order what is the most and what is the least relevant feature for the classification model. We start for the abstraction, so the immediate, the first step. We see the distribution of a feature across the data set that we have, and we determine a cutoff, which is a value under which we say that something is underexpressed or has a low value, and something is up, so is overexpressed or has a high value. This is a reduction in the entropy we carry over, so the information we actually preserve is lower, but this also guarantees a certain resistance to noise. Also, as we said, is compatible with Bayesian methods, so we can have a more intuitive representation, exploit some nice properties of this particular branch of probability and statistics. And this comes in handy, as we said, for the knowledge graphs. Knowledge graphs is a representation of a class that contains the conditional probabilities between pair of these discrete objects, which are called flips, by the way. So age up will be the flip up of the feature age. So we can link the flips about these conditional probabilities that starts to shape these interactions inside the classes. Now, once we have this structure, we can have centrality computed on the nodes like PageRank to identify the top players in each graph. This is important because also you may have something that is very relevant in a particular class and not relevant in another. We'll go back to this because it's actually a topic of one of the papers I wrote. And then we combine this PageRank centrality with the probability of the flip of appearing in a certain class. So we combine the interplay of the flip with the rest of the graph by its individual contribution to the stage we are in. As we said, this gives us a significance profile, so we'll have some flips being important, some flips being not important, and this is used for doing the pattern matching we discussed before. So this is the similarity matching. This is how we compute the graphs. So this equation in short few words, we're looking at how the proportions of the different flips across the classes is changing. So we're doing the difference between the proportions across the classes, and we see how much it is changing on average. The idea is that the rank is a score between 0 and 1. 0 means that the distribution, the proportions between the flips doesn't change at all across the classes. So it's completely useless for classification because you don't see any change across it. 1 is the maximum difference you can observe, which means that, for example, in class 0, everyone is tall. In class 1, everyone is short. You have a complete reversal of and a perfect discrimination of the class given this feature alone. So we try to compare this against machine learning. To do that, we use the standard machine learning methods, traditional, so logistic regression, random forest, ridge, stochastic gradient descent, and support vector machine. Later on, I also performed a comparison against XGBoost, which was a little bit more recent. We could say it's a little bit more trendy, given the results in the recent years, but it's a later comparison. And we tested this resilience against the missing data for different data sets at different levels of removed information. So this 20%, 40% means that we removed 20% of the values, 40% of the values. So we started making more and more fragmented data sets to see how these models were coping with that. Now, of course, some of these models, machine learning models, are not supposed to be run on incomplete information. So we had to run an imputer to simulate as filling the missing information and give it something plausible. Of course, the imputation is sensitive to the patterns in the dataset, meaning that it could impute correctly or not, depending on how the feature interacts with other things in that dataset. And more information is missing, the more difficult it is to have an accurate prediction because you have less information. So here we see how these methods performed across these levels of fragmentations for each data set for all the different classification methods. Now for calculus, we have two.
Luca, excuse me.
Yes.
Well, because these drawings are Well, relatively small.
Yeah.
Could you please comment about colors, because I
Yes,
try
yes.
to understand what they present.
Yes, so Cactus has these two classification modalities called probabilistic and PageRank, CPB and CPR, which are these pink and brown lines in the graphs you see here. The others are the remaining colors from orange, red, green, and purple, and blue. So we see in general that this has the purpose of showing that with the increase in the fragmentation, the general accuracy decreases, of course, but some have a steeper or smoother descent, let's say loss of accuracy with this fragmentation. So there are methods that are more resistant, methods that are a little bit less resistant to this phenomena. In general, take home message here. Now I highlighted the values, but I see that it's not very visible, but Cactus in these comparisons wins roughly 9 times out of 20. So almost half the times Cactus had a better performance than the standard machine learning models, which was a good first result. I will be a little bit precise with the next figure because we go on AMD. So after this, I continued expanding the tool with a little bit of a more precise objective, which was also applying this to AMD to have a transparent and flexible classification system. Now, AMD stands for age-related macular degeneration. It's a retinal disease that is focused on the macula and the fovea, which are parts of the retina. Essentially, is a decaying in the structure of the eye that causes loss of sight and ultimately blindness. Is a neurodegenerative disease, is also linked to Alzheimer, is a very long disease, so it takes quite some time to develop. As the name says, it's age-related, so it has a strong correlation with age. And it's very important to capture it immediately because it doesn't have a treatment able to fully revert it. So the earlier you get it, the earlier you detect it, the easier it is to start treatment to slow it down and prevent it from progressing further. So it's very spread worldwide. There are millions of individuals having it. It also has two different late forms. So not only takes a long time to develop, it actually has different end stages, which are called atrophic and neovascular, dry and wet. They can actually also coexist in the same eye. You can have one form in one eye, one form in another. So it's very complicated to actually deal with them because they are very different, but they are not mutually exclusive. They cause different things. For some of them, there are some more treatments. Some of them have completely no way of being cured. So here there is a brief description of this. Dry will be actually everything from the beginning of MD to this actually late stage, because there is an atrophic stage where simply you have a loss of focus due to lipofuscin deposits called drusen and atrophic patches in the fovea. So essentially you have these deposits on the retina that prevents you from receiving the light, and this causes loss of focus, blurriness, and everything. And there's no treatment opportunities. Wet is the creation of blood vessels in the back of the eye. So this atrophy, this is actually the creation of new structures. Problem is that these structures, when they are created, starts rupturing the layers of the eye, particular bark membrane, retinal epithelium. So you start having a loss of organization in the eye. And these are a different thing. It has some treatment options that essentially go to remove these new blood vessels, but they lose the impact over time. So that the biological response to this kind of treatment is not, let's say, permanent. So after a while, patients simply develop a resistance and they're not effective anymore. Plus is quite tricky because these kind of therapies are delivered through an injection in the eye, so it's not particularly pleasant. So there is also a problem of patient complaint to the treatments. So in general, it's very difficult to guarantee a high impact of the therapies to people over time. There are different factors in this disease. As we said, age is an important thing, but genetic is very important since it's also a long process. There are also a lot of elements playing a part in it. AMD is very based on inflammation, chronic inflammation of some tissues. So there are both genetic elements, particularly complement pathway, but also smoke and lack of physical activity can contribute to this accumulation of inflammation, oxidative stress, and so on. Diet as well, if you have an incorrect diet, it can actually contribute even more to this inflammation, chronic inflammation. So we use this dataset from IRISC, which is a consortium of universities, research centers across Europe. So it's an harmonized longitudinal study on MD progression across Europe. They have multidimensional data, so genetic, retinal images, dietary information, demographic information, clinical data. There is a lot of data in this. And we wanted to see how this, if this data would allow us to create a system to detect AMD before retinal images are captured. So the important point here is to consider that we are not using retinal data because they need time to be acquired. They cannot provide AMD classification before the first symptoms are appearing, which can take some years also. And they require trained personnel. There is a lot of overhead about the collection of retinal images. So our research question was, can we do something that is able to detect AMD without using retinal images? Now, retinal images is the main way of classifying AMD. If you go to a retinal specialist, the only protocol to detect and diagnose AMD is to retinal images, but we were curious if there was something in this genetic, dietary, clinical data that will allow us to detect AMD. Consider that there are 5 stages of AMD, so this is a 5-class problem. So despite you see here a quite low balance accuracy, keep in mind that the random chance is 20%. So at top, we're almost doubling the random chance, which is not super bad. And we did the same framework as before. We tried more and more information removed, and we tested how these algorithms were reacting to it. In addition to the previous experiment, we added a degree centrality. So it's not only page rank, but also degree centrality. This is because degree is a local centrality metric, meaning that it only considers the connections of the node to the rest of the network. It doesn't consider the structure of the network itself. So the hypothesis here was also that in some cases, it could be more accurate, especially when the network structure becomes particularly alterated. It could be a little more resilient to missing information. And we're also adding XGBoost, which is a little bit more state of the art for what regards machine learning classification. So as we see here, I hope Marian is a little bit bigger. We have 3 classification modalities from Cactus, which is a green, blue, and orange. And all the rest of the machine learning approaches are done here. And we can see that across the additional missing values introduced in the dataset, the performance decays a little bit, but we can see that Cactus is always able to provide a solid representation and classification of AMD, which was a very positive result. So in general, we see that for the first 3 versions of the dataset, PageRank was the best. Then from the last 3, degree started, and also probabilistic started being more effective in classifying AMD. This, as we said, is probably because there are in certain networks alterations after a certain alteration of the network, these classification modalities start to have different effects. So probably PageRank couldn't handle a very fragmented network, while the other modalities could. So that was an interesting result. So also after we performed this classification, we also wanted to see how this could be used in a real scenario where a clinician or a user wants to understand what the model is doing. So as we said before, we have the ranks that show us the most important features for predicting AMD. Now, age was the top one, which is actually very good because, as we said, is probably the most important thing to develop AMD is being old enough. And we also see that people tend to be more and more older and older the more they progress to AMD. So this was a very good result that the model was providing us with. Also, we saw some genetic information. Of course, this variable is visual acuity. So the lower the visual acuity, the higher the probability of having AMD, which makes sense because you have a degradation, a loss of sight. In general, a lot of genetic elements here, but also some supplements in the diet. And this was a bias that we identified thanks to these ranks because people with advanced AMD are more likely to be prescribed and have supplements to slow down the progression because zinc and vitamins can provide some resistance for development of AMD. And this is a bias because it's not a cause, it's an effect of AMD. So after we inspected these ranks, we saw this as a bias, as a confounding factor. So we ran Cactus on a refined data set, which is this middle column, and we lose some accuracy, but actually in some metrics, I agree, we lost 7%, which is quite a lot for these proportions, right? But probabilistic and PageRank all lose almost nothing. So we wanted also to do a further step, except from, of course, removing variables that are not important, that are not really related to AMD, because they are an effect, not a cause of it. Can we also focus on the most important features only? So we wanted to do a distillation, what is called distillation. So from a big model, we wanted to focus on the most important feature, and we saw how the accuracy was changing, right? So instead of having 50 features, we focus on the top 9 ranks that Cactus was giving us, and we essentially lose 3-4% by sometimes in accuracy. So we also wanted to see how important were the top 9 features, essentially, how reliable Cactus will be if it was provided only with the most informative feature without anything else. So again, this is to test the hypothesis that the classification is resilient to missing information, and it was quite okay. Second step was the confidence. So the question is, when do I trust the model? When I get an output, when do I decide whether I should trust it or not? We decided this was not an easy question. It probably is not even a question that has an objective answer. This depends more on the practical constraint you have, in particular, how bad it is if you are misclassifying someone, and what is your, for example, your availability to collect further data and run the diagnosis again, right? Because of course, as we said, Cactus is able to perform on missing data or small data sets, but if you have a diagnosis you don't trust, you can do 2 things. Either you try another way, you go to a clinician, you do another test and everything, or you give it more information to the model. So depending on these constraints, you can actually decide whether you want to trust the model or not. So we wanted to see how the accuracy was related to the confidence of the model, where the confidence in this case is, as we said before. Okay, now I want to write. So we said that when you do classification, you do the similarity towards each class, and you assign the highest, right? So the confidence in this sense is how heterogeneous the similarity against each class is. The idea is that if you get a very high similarity against one class and a very little similarity against the others, the model is more confident. It's easier to make the choice. There is less room for uncertainty here. While if you have a very similarity, there's more room for it's easier that the model is wrong, right? So this is how we compute the confidence, how heterogeneous the similarity distribution is across the classes, and how this relates. So this goes from 0 to 100, where 100 means of course, this is normalized, but this means that the significance towards one class is much bigger than the other. So it's a little bit like the ranks, right? The more different the distribution is, the higher the score, and vice versa. So the more confidence the model is, we see how it relates to the balance accuracy and how the confidence is assigned to the population, meaning that how many people are in a certain confidence range. Now I'll get there. So first of all, we saw the relation between confidence and balance accuracy. And we see that on average, the more confident the model is, the better the accuracy, which is this. So in yellow is the accuracy in this particular range. So 80, 90 here, for example, % of confidence. The cumulative is essentially this area. So if I start including people I'm more and more confident about, how is my accuracy changing? We saw that in general, long story short, that the more confident the model is, the better it is, which is not bad. At least is a starting point. And also how these people in the dataset were assigned confidence. So we saw that in general, some models tend to give more confidence than others. So here we have a more skewed distributions. Here we are more normally distributed values, which is good. Better to have normally distributed values because you are more, you can trust the model more when it assigns a confidence if it's not skewed to the right, because otherwise this means that the model is simply assigning a lot of confidence even when it shouldn't. And also we started having these distributions compared to the confidence. We could see where some quantiles in the populations were. So how much confidence do I need to cover a certain part of the population? And what is the corresponding confidence I have? So it's a trade-off, right? The more accurate I want the model to be, the fewer people I can trust the decision on. Vice versa, if I accept more certainty, I can cover more population, but I will also be less accurate, right? So we saw that to cover 90% of the population, you will get an accuracy of 25%. If you want to be very picky and cover just 50% of the population, you will get an accuracy of 30%. So there is a trade-off that here was described, and it's quite important to have. So conclusions, there was a study of how accurate these models were in screening AMD before the actual clinical tests or retinal images were acquired. This was the simulated scenario. And we saw that we get better results than standard machine learning models. But of course, the first step, because the accuracy is not still not reliable for clinical use, but it's a good big step. We also understood and discussed this problem of including people in the decision, informing them, making them decide when they should trust the model or not. It's not so easy, not so straightforward. And we discussed how this had what kind of implications this had on adoption of these kind of models in clinical practice. Next, we wanted to use the longitudinal data set we have in AMD to see how the genetic profile was changing. So there were different trajectories inside AMD, and whether we could capture them with graph theory. So this is the data set we have. So we have 5 visits for 5 different AMD stages. And we can see that people tend to get a little bit older across the study, of course. So the study took on average 25 years. So in 5 visits, every 5 years there is a visit. So people tend to get older and also tend to get fewer. So you start to drop more and more people the more you go across the study. There was some new recruitment, we would say, but when you have a longitudinal study, you want to focus on the long trajectory. You don't care if some people in the meanwhile join the study because you don't have enough data points then. So we wanted to focus on this kind of data to see what was happening from the point of view of genetic, but we also had the problem of having a quite limited sample size, especially in the late visits. So we're starting from that. So we built a tree that described the progression from the first healthy population, so from these 7,000 people, across the different visits. So we saw how they progressed across the 4 following visits. Some of them progressed, some of them stayed in the same stage, some of them progressed in a different visit than in another. It was quite, I would like to show you, but for sure it wouldn't be very visible because there are a lot of bifurcations over 25 years. They created a lot of bifurcations. But what we did then was we saw the genetic profiles of these populations that were starting to progress to different stages. And we started wondering what caused this progression in genetically, what was responsible for this, if there was a genetic factor responsible for certain populations progressing to different stages, staying where they were. So we did a knowledge graph representing the interaction between genetic polymorphisms in each stage. So we saw how in healthy people some genetic variants were interacting, how much related they were in these graphs, and whether across different AMD stages there was a noticeable change in their centrality. So we can see, first of all, that this is a pairwise progression. NP is people that never progressed to any other stage, while stage 0 were people that actually progressed at a certain point, and then they went back, probably misclassified or uncertain in the classification process, but we wanted to treat them as different groups because we want to see also if there was something actually going on there. And we actually saw that there was a variable that was acquiring a lot of centrality in this second group that progressed and then went back. Meaning that maybe there are also some mechanisms that cause this apparent progression to AMD, and then these conditions solve themselves. And in general, the more you progress across the AMD spectrum, we can see that the more changes are happening. So there are more and more things acquiring and losing centrality in the disease, which was also interesting. Meaning that the entropy in these graphs was also increasing. They were becoming more chaotic. They were changing more and more. While at the beginning you had very small changes, even between stage 0 and stage 1. Then you start to have more and more things that are starting to get to different shape. So by looking at each of these stages and the centrality of these polymorphisms, we wanted to see which of these were showing a steady change. So there was someone here that was constantly losing centrality, so was becoming less and less important and related to advanced AMD stage, or conversely, if there was something that was acquiring centrality, so becoming more important in advanced AMD stages. And of these 52 genes, 130, I think, genetic mutations, there were 21 that showed this steady pattern. So this was a perspective that we used to find potential targets for AMD due to the constant increase in the AMD, and conversely, what could be a protective element for AMD against AMD, since they are disappearing the more the disease is progressing, meaning that fewer and fewer people have this particular mutation, the more they progress, okay? This is very important because usually when you do a study like this, you do a GWAS, a genome-wide association study, but you quantify the contribution of each mutation alone rather than seeing how they interact. So I think it's also important that we consider this because you capture the interplay, not only the individual contribution. So I think this was a very interesting effect and a very interesting finding for AMD, because this is a multi-stage and multi-dimensional disease. It's important to capture the interplays between different elements. Now, going back to the classification thing, we saw that in some cases, Cactus was able to provide a very good accuracy. In some others, no. So it's obvious that probably there are different properties of the data set that are captured by this model compared to the other machine learning models. And we were wondering whether these were complementary, if these two perspectives on the data will be merged, aggregated, and whether this will provide better results. No. Now, there is an important social phenomenon called the wisdom of crowds, which is a principle saying that when you aggregate independent observations and you average them somehow, this usually outperforms the best individual prediction in the crowd. So if you have even if you have experts and common people doing a certain task, if you aggregate their observations, they tend to be more reliable. Of course, there is some assumptions for this to work. They need to be diverse, so that people need to have different perspectives, different backgrounds, different assumptions about the data. They need to be independent. They cannot influence each other, decentralized, so then there cannot be a person that is influencing all the others. But as long as these principles are more or less active, respected, this can happen. So we wanted to transpose this concept to machine learning and see if the same was applying. Of course, ensemble classification is not something we invented, it's something that's been along for a while, but a fundamental question that I had, for example, was the diverse aspect of this phenomena in machine learning is referring to diversity in the data you use to train the models or diversity in the models themselves. So I wanted to investigate two kinds of ensembles. One composed of different Cactus instances trained on different portions of the dataset. So a little bit like random forest. You have trees trained on different portions of the training set, usually through Bootstrap, for example. And it's Eugene's ensemble. So the dataset is for training is only one, and every method is trained on the same dataset. We use R voting, so it was a very preliminary result, but we wanted to see if this was what was happening with a very simple experimental scenario. R voting means that each outcome counts as a vote. You don't care how confident each model is. You just take one and only outcome, and then you do you take the mode, right? The more frequent outcome given by the models. And we applied this to 4 different data sets, and for each of them we tried the different ensembles. So of course for the heterogeneous, for example, we tried combinations of 2, 3, 4, 5, and so on until 9 models. So all the possible combinations of their outcomes, and we took the best. We took the homogeneous, the best homogeneous ensemble also, and we compare it to the best single model on the dataset. So we saw if actually we had an increase or decrease in the performance. Actually, so delta heterogeneous would be the difference between the best heterogeneous ensemble and the best single model. So if it's positive, means that the ensemble was actually improving the accuracy. Negative means that the ensemble was actually performing worse than the best single model. So in 3 out of 4, the best heterogeneous was performing better than single model, while the homogeneous was losing accuracy all the time. So there was already quite clear pattern, right? Diversity in the data in the models is more important than diversity in the data, at least for this scenario. Of course, with random forest, for example, this works even then being homogeneous, so the same kind of model applied to different datasets, but because those are very simple models that tend to overfit, and the trick is that by having a lot of trees, you provide them with variance, so you act against the overfitting. If you also use XGBoost, for example, you still have this creation of simple trees, but you reiterate the creation of trees to correct the mistakes of the previous model. So the algorithms with trees, for example, are designed to balance each other by correcting their mistake or by increasing their variance. So there is a slightly different approach, but in general, we saw that heterogeneous in this case was better. But I wanted to see what happened, why in 3 out of 4 it was going better, and then this was a 10-fold cross validation, 20-fold cross validation, sorry. So it was quite statistically, I mean, this was the average, so it was quite stable. We wanted to see why this happened. So we did a TSNA using the properties of the datasets. And we saw that there is a certain pattern because the only dataset where the best heterogeneous ensembles was going worse was the heart disease, which is the smallest and the one with most classes and the least features. So doing a TSNA, this was here. And going up along the second TSNA component, you have the datasets with more and more with less and less classes. So the more classes you have, the more you're likely to see these. The fewer classes you have, the more likely you are of observing better accuracy from heterogeneous ensembles. And with a Pearson correlation between the second TSNA component and these values, we got 86. So there was a correlation between these two aspects: complexity of the data set, of the task, and performance of the heterogeneous ensemble. So we see also here how the best performance, the performance of the best ensemble for each size, so 2, 3, 4, 5, up to 9 models for homogeneous and heterogeneous, was relating to the balance accuracy. And interestingly, you see that there are 2 different behaviors. In homogeneous, you tend to have higher accuracy the more models you have. So a little bit like random forest, you increase the variance by adding more and more models on different data sets. In the heterogeneous, you actually tend, after a certain local maxima, to go down. You start to lose accuracy when you increase more models, when you increase the complexity of the ensemble. And it was interesting. We can also see the composition of these ensembles in terms of where they were the best. So we see that each data set had different length of the best configuration. These 3 had the heart disease, which was the only one where the best, the single model was the actual best, is 1. The best configuration is 1. The others are 3, 3, and 6. So different lengths. There's no, let's say, common length of the configuration. And when you see the number of best configurations each model appears into, now I colored this to match data set. So you see where each model was the best. There is no single model belonging, appearing in all the best configurations. But interestingly enough, the three cactus classification modalities together always appear in the best configuration. And this is a preliminary result that later I encountered in different things. The tendency of cactus of always appearing as the best in the best configuration, in the best group of algorithms for an ensemble, which confirms the hypothesis that it was providing a better complementary perspective on the data that was able to improve the decision of the ensemble when it was available. It was also interesting because alone was also the best performance in one dataset. So this is kind of a result showing its role either as an individual classifier or a team player, a member of an ensemble performing classification. And we are now exploiting these results in different areas, in different datasets, and we're finding confirmation of these results. Like with Jamal, we have one with stroke, where we found this happening. Cactus was not the best alone, but when you combine it with others, it gets in the best group of methods. We also have a project with Sheffield on placenta classification, and the same happened when you start to put cactus in the group of methods, performance gets better. So in general, there are some properties that cactus was able to provide during its development. So there was a good performance for the classification of incomplete noisy dataset. So we managed to make something that was able to provide good performance even when the data was extremely limited. There is a promising impact on ensemble classification. We want to study this further also in terms of, for example, resilience of the ensemble. So what happens if one or more plays in the ensemble become unavailable? What happens to the performance? We want to do a general review of cactus. Now we're doing also some experiments on the abstraction phase. So how more refined mechanisms to partition continuous values into discrete symbols, which are also used in other projects. And in general, we're also doing expansion of cactus to use it as a model used by other frameworks to do reasoning, to do update of the information with new data when new data is coming. So in general, this became the foundation for more things happening in our team. I'm happy I could contribute this, and more exciting things will also come in the following years, because now we are also becoming aware of the potential implication that this has in a broader area. Thank you. Please, if you have questions, let me know.
Thank you also on behalf of people who are on the line remotely.
Yes.
Well, really, we have time for questions for discussion. Yes, so I think that we can do arrange this in such a way that you please, Luca, observe questions from the audience first, on the third floor, and I will try to look at what is going on remotely from something like almost 20 participants online. So, but before we will go there, I have a question about. Well, I in order to understand what you have done, I need to make a kind of separation between elaboration of the tool, which is the cactus. So, because a part of your research was elaboration of these tools and finding out to which extent it is usable. And so this is, I understand that this is one part. And the other part, according to the title of the talk, Well, you have used this method and tool for, and according to the title, to predicting and understanding complex degenerative disease. So, well, so maybe it would be good to know on which basic, let's say, statistical probabilistic theory or statistics cactus is built, and on the other hand, which diseases, besides of this problem with eyes, you have investigated.
Yes. So as you noted, this was a combination of technical thesis where I developed a tool that was solving some fundamental questions. So it was fundamental research, and also application of these findings to certain scenarios to solve more specific questions related to the domain. In general, Cactus is a tool that combines the discretization properties. So this mechanism allowing to simplify and reduce the complexity of continuous variables into symbols that are more understandable, less susceptible to noise and everything, with a graph representation. They're also called Bayesian networks, where we could see the interactions between these discrete elements. So this goes to answer what kind of statistical approaches, statistical frameworks Cactus is built upon. And also from the practical implications, right now we have applied Cactus to a certain amount of scenarios. So in general, other than AMD, we applied Cactus to the prediction of allergies, for example, in a hospital we are collaborating with, which is America. So
yes, I know.
Prediction of allergies in children, and also to actually characterize and capture the heterogeneity of clinicians in this hospital. So we did a paper where we use Cactus to approximate each clinician's decision-making process. And then we studied how different these models were, whether they were sharing the same beliefs, the same confidence when they were looking at the same patient, or whether they were looking at, they were considering different things to be important. And what we found was that actually there is a lot of variability in what each clinician was considering to be important, which is also a very practical implication and direction to build on. In terms of, let's say, domains we try Cactus on, we have currently doing projects with kidney disease, so kidney failure and stroke. We tried Cactus also on data on dementia and also on liver cancer. So in general, we tried Cactus to several different domains with several different kinds of data, and we found that its structure, its way of working, also the description of its internal state was also actually useful to explain the result to clinicians or other users.
So I understand that that Cactus is becoming a kind of a universal tool, which can be even used for, let's say, I don't know, at banking for fraud detection, because it is just analysis of data, yes?
Yeah, it was built to be a research tool, so it had to be quite flexible and customizable. So it actually has different options to be used and set. There is also actually a web interface to use Cactus online. So as a web interface where you can enter parameters, tell Cactus how you would like to analyze the data set, and it performs automatically the kind of analysis you want, and then gives you the result in a let's say graphical interface. So yeah, we did some efforts in also designing something that was actually possible to use for different kinds of users. Yes.
Well, okay, many thanks. Now we have Janek Fischer with a question.
So I have a little bit of a follow-up question. So were you thinking about implementing Cactus in any like Open Python or any other language library for others to use it, or like open source? And the second question is about state of the art around machine learning with missing data. So what are the biggest opponents for your approach that are around?
Thank you for your question. First of all, to answer the first, no, I'm not planning to make Cactus an open source project because it's involved in some commercial projects in Sano. Also, in the next seminar, I will have I will describe a project where I'm using it. So, fortunately, it's not going to be released outside yet. Unfortunately for the other people, but to my advantage, it has to be it has to stay a little bit more commercial. And second, yes, there are several models that are becoming more and more able to deal with missing values. One example, for example, was Random Forest and XGBoost that I compared Cactus against, that are able to work even when some data is missing. I'm aware that there are also different methods able to do this in the literature. I honestly also wanted to do a very not say comprehensive, but I wanted to compare it against the most common techniques to see how it was comparing against them. I know there are also some specific tools, but I focus only on this because also I wanted to also understand why the performance in some cases was different. Like now, an open direction I have is having these ensembles that are able to perform well on certain dataset. I noticed that their structure changes, their performance changes dramatically if one or more of its members is removed. It becomes offline, for example. So now a very close and research direction will be understanding where each model performs better in order to understand and guess beforehand which models will be the most effective for the particular dataset at hand, for example. So this right now is my immediate direction, I will say, but I also would like in the future to focus on different methods to also combine with Cactus because I'm also curious of how they can interact together.
Okay, thank you. So basically the best out there from the well-known ones is XGBoost for missing data and Random Forest.
I'm not sure it's the best. Is for sure one of the most used methods for this. I started by considering by comparing it against common frequently used models. I didn't go too much into the niche, but
Okay.
yeah.
Okay, thanks.
Thanks, Janko, for your question. And maybe with a way in which Cactus could be maybe available for different type of communities, you can follow a scheme which is applied by a team of Miran Livni with Condor, where they never distribute source code, but they in development of Condor they gather all let's say remarked requirements, and they keep one version of this Condor. And Condor is available for free for scientific research, and it is the license it is used for let's say commercial purpose is necessary to pay. So maybe it is to be followed. Now we have a next person to ask the question. It's Olaf. Olaf, welcome.
Hello. So unfortunately, I missed a little bit from the first part of the talk, but from what I gathered is that you have a selection of genes that you also analyzed as background for classification. And my question is, when Cactus is also for understanding, not just for prediction, so did you note any kind of crosstalk between the genes? That's the first question. So was there some correlation of combination of genes? And I think I can guess that the answer is yes from the profiles you showed. The other question is, can you pinpoint why they are correlated? So do you have the, let's say, system biology network of these genes investigated regarding, let's say, whether there are certain, let's say, common pathways, metabolites, whatsoever, that connect these genes?
Thank you, Olaf. Yes, for the first question, yes, there are definitely patterns where they are strongly interconnected. When I drew the conclusions for this paper, I noticed that most of these belong to the complement pathway, which is a very important genetic component of AMD. Essentially, is responsible for the activation of the immune system and is responsible for what is called a para-inflammation, which is inflammation is a mechanism used in biology for, as far as I understood, of course, because I'm not a biologist, but is used to guide the deletion of certain elements. So a certain level of inflammation is required to guarantee that what is not desired in the biological system is removed, is destroyed, and the chronic inflammation, so the excessive inflammation in the system, is what causes problems in AMD, because too much stuff is was now saying it very naively, but too much stuff is removed. So what is happening is that the immune system starts to attack structures in the eye, and this is what causes the degradation. So this was a very interesting result to me for what drives AMD, because it also has a certain, let's say, is in agreement with the literature, I will say, in general. What is also important is that AMD is, being it strongly genetically based, what happens is that different populations may have different genetic profiles. So, for example, when I checked for results in the literature for some of these mutations that I'm showing on screen, what happened was that in some studies, for example, on non-European populations, these were different. These were not relevant or even not significant mostly, but in some cases there were also some mutations that are considered to be relevant for AMD in European studies and none in non-European population, which was also very interesting because it suggests that there are some genetic interplays that are very different in different subpopulations. So this was a hint that characterization is important of these findings.
Okay, but yeah, actually, that was some of the things I would have expected. Actually, I'm a biologist, so an information that is something that we know also from many other diseases where we try to look for genetic linkage, and you were referring to GWAS, yeah. So one of the reasons that GWAS is failing is that for most diseases you get every gene involved that you can think of, more or less, and in particular, of course, everything that's along the many inflammation cascades. Yeah, so this is normally rather a confounder, I would say, than helping to understand what is causing the disease. The problem is that very often we do not find the genetic cause of a disease, because this is in very low copy numbers, and in many of the jivas we will not see those events. Yeah, we only see the high copy numbers that are a consequence of inflammation, for example. Yeah, where many genes are really turned on and do a lot of transcription. So another question I have is you said you have something which is a longitudinal thing where you put several stages, and there's really a lot of time between. So maybe also the stages are, each stage represents in principle a different model. So you say you do Bayesian networks, but there are dynamic Bayesian networks which have been used for these kind of sequential events. Do you use those? The dynamic Bayesian networks. We also use them, for example, when you do some kind of predictions along a protein chain, because also the environment of the respective residue changes over the chain length. Then you use the dynamic Bayesian networks in order to account for these kind of changing environment along the chain. So, and I could imagine that this is a natural thing that I would do when I have to consider things that have, let's say, long-term effects. Yeah, so over aging, probably those people accumulate a lot of comorbidities, and some of them may change their diet. You name it. Yeah, so there's a lot of things changing. So it's very difficult with a static Bayesian network to account for those.
No, definitely. In fact, unfortunately, in this dataset, I don't have access to dynamic data for what regards genetic activity, for proteomics, for example. I would like to expand this concept in another dataset where I have access to proteomics in order to introduce the dynamism you are referring to. Unfortunately, here I didn't have this, but I was still curious to see if I could capture a dynamic from a static structure. So it was actually interesting in a way. Of course, the relevance is kind of limited because it's a static object you're capturing, but so it's not particularly refined or characterized. But I think it was a good proof of concept that this graph theory could be a good let's say, offer a good perspective on these diseases.
Yeah, but you may have cycles. Yeah, you can't resolve cycles in Bayesian networks. Yeah, so cyclic dependencies are unresolvable in Bayesian networks. So you would have to have something like a dynamic Bayesian network in order to unroll them. So
yeah, that's also true. Yeah. Now here I use degree centrality, so I was more looking at the connectivity patterns of each polymorphism to capture what was relevant in the network and what was not. So in this sense, the cycles were not a problem, but if I wanted to do something about the dynamic of the network, of course, I would have to account for this as well, which is also tricky because there are cycles in genetic interactions.
Yes, exactly. Last question, what would be a relevant percentage? You showed something like balanced accuracy of between 33 and 40%. At what time would it be interesting to, let's say, domain scientists, medical people, really to start using those methods?
So I know that generally, so I'm moving here, a good clinical accuracy is around 80-90%, meaning that to be used as a clinical tool, usually that's the threshold that you want to pass to start talking about applicability in clinical scenarios. Now here, the important point I want to stress is that this is supposedly a preclinical scenario because we're basing this classification only on information that is not, let's say, clinically used for classifying AMD. So as I said before, usually retinal images is the only accepted way of diagnosing AMD, meaning that without retinal images, technically you don't have a protocol that allows you to have a formal diagnosis of AMD. Why this approach is important is because it doesn't assume this to be available. So it's focusing on what happens if you don't have anything available, which is the case when you want to do a screening of a population so you don't have the time and the resources to collect and analyze retinal images of thousands of people. And or maybe you have a screening for multiple diseases, so you cannot focus on the specific test for each condition, but you have to use commonly available information. Or we can debate that maybe genetic polymorphism is not exactly a routine examination, but I know that now there are also a change in perspective actually, where is being discussed that a genetic, let's say, profiling of a population could be performed to search for genetic disease in a broad spectrum, right? You have a general high level genetic characterization of each individual, and then you use this to capture possible comorbidities. So this is something this is the assumptions we made. This is not something that a clinician will ever use, but this is not supposed to be used by them. It's more supposed to be used as a first step in a population to understand, for example, who is sensitive, who is possible, who is likely to have AMD, who is not, and with this result, guiding, referring this person for their examinations, for example. So in a way, it's supposed to be an optimization framework, an optimization step to optimize these resources that are needed to have a more accurate diagnosis, a proper diagnosis, actually, I would say.
Okay, well, I'm very sorry because we have a queue of people who ask questions, who would like to ask questions. So, Olaf, well, maybe offline will be possible because now we have Wiesław in the queue. Wiesław, go on with your question, please.
Thank you, Marian. Can you hear me?
Yes,
we can hear you.
Okay, fantastic. Thank you, Luca, for your presentation. I think it's very wonderful that you are focusing on a specific clinical applications, and my question is related to AMD. This is a specific case. A patient got wet AMD. The patient is 70 plus, an artist, and it suddenly changed in eye. So of course it's very unfortunate. The patient went to the renowned eye clinic in Warsaw and was told that the person had to take injections in eye. This is the treatment of AMD. 6 injections a year over 3 years. One injection costs 2,000 zlotys, so it's a very expensive treatment. And of course, usually the doctor says it will be for your whole life. Yeah? But the patient somehow took one injection and changed the lifestyle and took more supplements. And after a few months, the vision was back to normal, and after a few years, it's still normal. So the question is your model is able to explain this case because the patient acted against the clinical practice, and at the end of the day, the result is really very good.
Yeah. So I will say that in general, I could, by doing the classification at the time the patient was prescribed the injection, and after the time you said, after a year or two, doing another data collection and putting it in the model, I will say it would explain what happened and what made the classification change, and therefore what changed in the big picture. So another, I think, good point of using abstractions is that you can quantify changes in this sense very intuitively. So you could explain this by saying a particular biomarker in the blood is much lower, another one is much higher, and then you compare this against the literature, and you see that these transitions are actually meaningful to explain the change in AMD. I will say on let's say, a political level, it would be possible with my model because it shows actually what is important for the model to say this person is healthy, this person has AMD, and so on. So I think it will be possible.
Yeah, because I believe in this way, if you can help this kind of patient to predict, okay, no need to take so many injections and you can save so much money, it will be a powerful tool for the patients.
Yeah. We actually consider for a while now, it's a little bit in standby, but maybe we'll come back one day. We consider the usage of this classifier also to describe how a patient can jump to another stage, another state. So since there is a similarity score that the patient has towards each class, and you perfectly know when you compute this similarity score what is more important to move to a certain class, you could quantify first of all how far the patient is from another stage, from another profile, and then you can also quantify what is more important to change to make the patient jump, right? By seeing what, for example, what features are more discriminative across these two classes, and in Cactus you have it because we have this graph representation of the disease stages. You can actually measure and quantify what is changing the most, and this could be possibly a suggestion, a change to lifestyle, of course, assuming that this thing can be changed, because if it's genetic is not possible, but if it's something related to lifestyle or to diet or so on, it can be modified, and you can simulate how the classification will change, and therefore you can suggest it as a possible way to move from one stage to the desired one. Yes.
Yeah, okay, thank you and good luck.
Thank you very much.
Probably because we are reaching, we have only 3 minutes left. I think that we have time just for one question from audience on the third floor.
Question that I have, we can discuss it later.
Okay.
But
the question was if I consider the AMD stages differently, singularly, or if I did no AMD versus AMD. I treat them differently because I wanted to capture the different properties of the different properties of each AMD stage and see how these were different. Also, when I did the ranks, I wanted to see if there were trends, right? So people were getting older, the AMD score was getting higher, and so on.
But the question,
And now the question is if why I believe that joining Cactus with other classifiers is providing better results. This is valid as long as the classifiers make different mistakes. So the important thing is that by combining them, they can compensate for the reciprocal short sides, let's say, for their mistakes. So it's easier to correct a mistake when you have multiple models because you assume that most of the models are right when you vote. If you tend to have models making different mistakes, which was also finding that happened here, right? When I tried an ensemble made of the same models, the performance was going wrong, was going worse, because they tend to make the same mistakes. There is also an analysis that I didn't show here, but when I see the correlation between the model's decisions in the heterogeneous and homogeneous ensembles, what I noticed was that, of course, the homogeneous ensembles were more correlated, and this goes against this fundamental assumption that the observations are diverse and independent. If you have models, the same kind of model trained on the same on different data, but still, this is not enough to guarantee that they will make different mistakes. They will capture similar patterns most likely, and this was the demonstration in a way, empirically, at least in this specific application, because as I said, random forest, for example, or XGBoost actually make it their objective to do that using the same model over and over, but it's a little more, I would say, a specific case. Does this answer?
Well, okay. Unfortunately, it is the time when we just must we like to thank very much Luca for such a interesting talk.
Thank you.
To
See you
all
again also.
who take part in discussion.
Mhm.
So many thanks, grazie mille. You are all invited to the next seminar in a week from now. We will host Professor Marek Pruszyński from Nomater Center of Excellence for Nuclear Research, but he will be talking about novel radiopharmaceuticals. So, and Professor Pruszyński will be personally at Sano, so it will be possible to also to meet with him on our famous third law. Thank you very much, and
Bye-bye.
see you in a week from now at our Sano seminar.
Bye-bye.
Thank you. Bye.